more moments to give some info about our Diamond partner, Scream, an SQL analytics database built on GPU technology. Scream has broken the data analytics size and speed barriers, enabling enterprises to make use of their rapidly growing data stores. While many organizations struggle with analyzing their large volumes of data, Scream empowers them with fast, flexible, and scalable analysis of data from terabytes to petabytes. Scream brings queries that once took days down to hours, and those that took hours down to minutes, and it's the best tool in the market to reduce the total time to insights. Okay, now I gave you all the information, and David, we're ready for you.
Thank you. So nice to see everyone in person after COVID. It's my first presentation like this, and I'm so excited. We're in an era where algorithm is all around us. And as data scientists, data engineers, data analysts, it's our jobs, or maybe even our passion, to make them more accurate. Accuracy means better models, and that they're more sensitive, so they're trained to higher sensitivity. And this is the center of really what I'm trying to discuss with you today. AI, or machine learning, or deep tech, is a very hot topic right now, but it's been around for this quest to have artificial intelligence that can augment humans for the last 70 years. From theories like Alan Tuning's tests, Asimov iRobot, to like milestones such as beating Kasparov in 1997, Big Blue, or winning Jeopardy, all the way to Siri or Google Assist on our mobile phones. There is a big explanation, a big progression with AI, and alongside that as well, all the digitizations such as social media and moving business to the cloud. And in the center of it, it's all about data. We're trying to change the world with data, and a few statistics I just captured last week. It keeps changing all the time. Almost 200 billion emails sent every day in the globe. Almost 6 billion internet users running in the world, and so on and so on. And that generates a lot of information. And if you look at it from an enterprise point of view, from businesses point of view, look at what mobile phone did to telco with CDR data. Every text message, every call, every keystroke they're collecting. If you look at internet banking and how transactions for payments, once you be able to start sending money to each other via mobile phones, the enterprises go and accumulate more and more and more data. And what most of them are doing with it? Taking it and storing it for future use, right? Have you ever had a cupboard that you just got a lot of stuff and put for the future? You usually don't touch it. And alongside of it, all the progression as well in compute science. I really enjoyed listening to my colleague before. You know, the landing on the moon in the summer of '69, the computing power that was there, it was 8088. So one of the first Intel, one of the first PCs, that's basically what it took to land at the moon. It's about, I don't know, a mobile phone, it's about a billion times stronger than that. And of course, bandwidth. Look at just what the Wild Wild Web did for businesses, and now think about 5G and mobile phones, what we'll do for IoT data and any other things, autonomous cars, etc. And the fact that businesses moving from digitization into the cloud, that means they'll be able to start doing by far more digital processes, collecting by far more data. And all of these are augmented to some sort of okay, what do IT do with that? Because eventually data scientists, data engineers, data professionals are all dependent on IT. I think yesterday the event, I think Heidi kind of mentioned, it took like 6 weeks to get a machine into production. Yes, it's a governance issue, it's a complex issue, which all stems from the data. So what we tried to do when we try to use that data and to model it or to build an algorithm, usually you go through the classical, and sorry, I'm just simplifying it for just to make a point here. But you go through some sort of iteration, some sort of process. The data sits really in the middle. And as a good data scientist or data engineer, you know that you always start with the data. If you don't always start with the data, if you start with the model, you'll always have problems later on. And in the past, the data was relatively straightforward. Descriptive data, interactive data, some sort of a 360-degree of the customer. And then you would start modeling. The first thing that you do with data, you try to identify the data sources, then you try to do data discovery. And data discovery, in my opinion, is the most important element of any model building or any algorithm building. Because, yes, you do need to understand the business logic, yeah? But eventually the model, if you're using a Sigmund Freud or a function or anything like that, doesn't really matter. The logic is eventually embedded into the data. So understanding and discovering the data is the most important thing. And then you need to cleanse it. You think that structured data or tabular data is clean, but in many, many cases it's not, just email addresses. Sometimes you can put semicolon and put another email address, etc., etc., etc. So if you're a data scientist, you probably know that you really need to look into it and start cleansing the data, and then you need to start transforming it to something that you can basically start building a model from it. So all of this is traditional. I'm not teaching you how to suck an egg here, but this is basically what's done. And then you're building the model. And when you're building the model, again, you need to look into the data. You try something, you change something, you run the data with it. So the data is in the center of building accurate model. And the data is in the center, later on, of training that model to get it to a higher accuracy. And of course, once you come to integrate the model to real life, to production, you need to access that amount of data. So where's the challenge? As I mentioned, the data is just keep exploding, yeah? It's coming from so many different varieties. If 10, 15 years ago, if you're a bank and you try to do fraudulent transactions, you probably would only look at your data sets. If you're a bank right now and try to look at fraudulent transaction, you probably would connect to other APIs like social media to see if the person is really traveling, etc. Well, it's not as easy as that, but I'm just making a point here. You start to enriching the data with a lot of different data sources. And as data is the new oil, organizations just accumulate more and more data, which is great as an idea, but how do you practically use that data? Because it's like silos of data, and it's a really huge amount of data. All the analytics tools that in the world that basically were designed in gigabytes or maybe a few terabytes of data, and customers now have tens, hundreds of terabytes of data. We have customers as well with petabytes of data. Think about IoT, sensors, assembly lines. Think about how much data these sensors basically omitting. And the data center or data lake or data store, data ocean, I heard so many different, data lake house is the new thing. Eventually, it's an amalgamation of a lot of different storage devices. And when you're trying to start building the models today, one of the challenges is how do you access that data? So because it's so complex and it's so large, usually they will put some data engineers to go and take a copy, and you're going to start working from that copy. Lots of issues with it. First of all, just the fact that they're taking and creating a copy, they're tainting the data. They're manipulating the data in some degree, right? Or they're giving you a small subset of the data to build a model, and then later on to integrate it. We all know how that's going to go. So that's one thing, but it's done not because they're trying to restrict the data scientists, just because of the sheer size of the data that it just makes it inaccessible. And data scientists usually kind of complain that the majority of the time, it really is data engineers. 70, 80, 60, I saw so many different numbers, but we talk to so many customers, so many data scientists. This is the number one thing that is spending all the time on transforming the data, preparing the data for them to start modeling. And this is just in the beginning. Think about it, modeling is not a one-off process, it's a continuous process. So you're spending all your time on data modeling, on a preparation. And then when you try to build the model as well, you try to interrogate the data, you try to understand the data. So if you have more data, your understanding, your insight that you will get from the data will be better. And this is really what will put us in a scrim. What we have done, we tried to find a better way to deal with large scale of data. Today, all the databases in the world, analytics databases in the world, are built on in-memory data architecture. Very high level, you take the data from storage, you load it to memory, and you let the CPU run on it. It's fast, it's efficient, but there's a limitation of how much data you physically can put on a RAM of a single machine. And as a result of that, Doesn't matter if it's Cloudera, if it's Exadata, if it's Snowflakes, if it's a BigQuery, if it's a Redshift. Doesn't matter what is the engine, they're creating multiple servers, multiple instances, because they need more and more RAM. And that makes it complex. That makes it complex to query it, that makes it complex to run it. And even if something like BigQuery is really good at hiding this complexity, it comes with a really large price, because you're using 400, 500, 600 servers to access 10 terabytes of data, or 20 terabytes of data. And that has a huge cost. So what we have done in Scrim, we build a SQL database on top of GPU architecture. We remove the memory, and we're taking the data directly from the storage device into the GPU cores. Think about it this way. In all other technologies apart from us, if you try to make salad, you use food processor. You take all the vegetables, load into the food processor, put the lid on, press the button, take the lid off, take the salad out, put the next batch of. This is how would you work in memory. With Scrim, you probably will have a conveyor belt that the vegetable will come conveyor belt, and thousands of knives will fall into it, and it will continue moving. So this is the real difference with what to try to build in Scrim. It's very much what we're trying to do is very much like what jet engines did to the aviation industry. Before that, to scale out, you used to use another propeller. So, but a propeller will always come at a cost. The cost of fuel, cost of weight, cost of range. While a jet engine, still a plane, still an engine, doesn't really make much change in terms of steering it and so on, but can go much longer range or much faster. So this is what we tried to do. We build a SQL database, which is standard. You know how to use it. It connects to everything that you're using today. You know how to interrogate it because you know SQL statements, but it can access a lot of data and do it really, really fast. This is kind of just a summary of really what we've done, like in a very highlights, which is, first of all, high parallelism on a single node. Of course, you can have multiple nodes, but that single node is really important because once you start working with data and doing things like joins and things like that, you really don't want to have a lot of data latency between multiple nodes in the network. So having it on the same bus, running it on the same system, reduces sometimes 30–40%. But more important than that, we do consolidation of servers on a single GPU card. You probably know you have thousands and thousands of cores. NVIDIA V100, 5,000 cores. NVIDIA A100, 8,400 cores. Think about it. If you take 4 GPU cards, putting on a single node, 20,000, let's say V100, 20,000 cores, equivalent of a mainframe in terms of power. Okay, so this consolidation of compute or minimization of compute is really important. We have a big customer, a big telco in South Korea called SKT. They took 4,000 execution servers from Cloudera and consolidated to 16 servers of Scrim. Large servers, 6 GPU cards in each server, 800s, really big machines, but still 16 machines to 4,000. Just think about the time it takes to manage the data center and licensing and upgrading and downfolding, everything like that. You reduce complexity significantly. More than that, it can scale. The way you deal with 1 terabyte of data or 20 petabyte of data is exactly the same. You don't need a new methodology. You don't need a fleet of data engineers to sit and prepare the data for you. Just simply open your studio, open your notebook, just basically start writing SQL code into it. We don't really have any limitation in memory, so we don't have any limitation of data. We have customers who generate 2 petabytes a day, and they're growing over the last 6 months. If it doesn't run fast enough, add another GPU card. It's another 5,000, 8,000, 20,000 cores. It's relatively very easy to scale out this way. It's really, really fast to try to query data on a really large scale, whether it's batch data or stream data. Think about all IoT and devices and all the data they generate. And as well, if you need to cross-reference, you need, for example, to join data that comes from stream with batch in a real time. Let's say you have a Kafka, Confluence, event-driven architecture. So it's very simple, very quick to do this sort of thing. And it's a minimum footprint from a compute, but as well from CO2. And so it's a green technology, which is very, very important for us as a company. This is the results. You can analyze much more data, much faster. You reduce emission and you reduce cost because you minimize everything into 1 single machine or 2 single machine or 3 single machine. It can work in a cluster of course, high availability, and with all of that, but it's a much smaller scale with much more power. And the value that it adds is predominantly in the four main categories. First one, the most obvious one, is to make things faster. So for Barclays Bank in the UK, Barclaycard, one of the subsidiaries, we try to do fraudulent credit cards for them. They try to enrich the data with 36 different data sources that they got externally. It was sitting on Hadoop, 78 clusters. That joint took 3.5 weeks to run. We managed to do it in an hour and 20 minutes. How do we do it behind the scene? How do we take 3.5 weeks and moving to an hour and 20 minutes? They had 4 GPU cards, so 20,000 cores. We take a very complex SQL statement behind the scene, the technology, breaking it down to 20,000 pieces of code. All of it is executable in parallel and run in rendezvous after that. This is how we think it can take 3.5 weeks and bring it down to an hour and 20 minutes. This is something that I didn't really say. When we say analyze things faster, we don't mean by 10 or 20%. We mean by a factor. So something that runs days will run minutes, something that runs minutes will run seconds, etc. At least by a factor. Second part, we enable you to analyze by far more data. So we have a big customer in South Africa. It's a big credit agency. They collect data on customers for the last 30 years. They needed to run some sort of really complex retro analysis on the data, but the data stack enabled them to do it only for the last 18 months, year and a half. Why? Because the machine just collapsed, just crashed after that. Just doesn't do the machine just hangs. We managed to do it faster than what they done 18 months, for 120 months, for 10 years. So it managed to enable them to increase the window of analytics and see by far more data every time when they're running those Windows functions. SQL joins, which is the next part about multiple dimension, is one of our sweet points. In memory, SQL joins happen in memory, that multiplication, Cartesian multiplication. And that means that you need to get data in and out. What happened in Barclays, those 3.5 weeks, the majority of the time was about cache in, cache out of memory to build that matrix. In Scrim, we don't do it in memory, we do it at the GPU level. So A, there's no limitation of how many SQL joins you can put in a single statement. We have customers running with 90, 80 SQL joins. And B, if it doesn't run fast enough, just add another GPU card to the mix. And we have some incredible results with that. If you come and see a demo at our booth later on, we can show you some really complex SQL joins with order by and group by, and really things that would take normally on a really large 67 trillion records. You will see that, and you see the result in seconds. Sorry, million records, not trillion. You'll see the result in seconds. And the fourth pillar, and it's probably, if you ask me, it's the most important one, especially for data scientists. It moves the whole interaction and dynamics in analytics and data science from batch, so something that you press and go home and tomorrow you get the result, to something which is ad hoc. You need to interrogate the data to build a better model, run ad hoc queries. You get the results immediately. If you're a data analyst and you don't understand query, build a Tableau or business object or whatever it is, and that will drill down it for you. Come again, we'll show that to you at the booth, a demo for that. So the ability to run near real-time analytics on a really large scale is the #1 tool the data scientist wants to work with, because they don't need the intermediary of data engineering that will create the data for them. They can go directly to the trusted data in the data lake or in the data store. They can understand it. If the model changes, and the model changes all the time, look at COVID, what COVID did to most of our models in the world. You need the ability to go and understand and interrogate the data as quickly as possible and get that result. Scrim is a SQL database. So if you know this SQL, you know Scrim. If you have assets that already use SQL, they can already use Scrim. I mentioned like sub-business object, for example. We have a big bank customer. I mean, almost every bank in Europe have hundreds of sub-business object lying around and dying to get rid of it, and they can't. We just went and changed the Oracle layer, just a new connection string instead of Aura net. We did the equivalent in Scrim, and we managed to accelerate that performance of those dashboards in 4,000%. So anything that you'd expect that should work with SQL will work in Scrim as well. Any kind of data source, any kind of ETL, any kind of data type that you're using today, you should expect it to work with Scrim. There's nothing new in it. We really try to keep how people using it exactly the same you'd use any other database today, just change the core of it, the engine of it, to be a bit more efficient. Scrum works fully on-premise, and it works natively on each of the clouds, so Azure, GCP, AWS, Alibaba, Oracle, almost soon we're going to have as well SAP, and it works in a hybrid. So we have lots of customers, for example, Vodafone, that a lot of the data sources sit on-prem, but the analytics or the consumption of analytics, for example, for customer churning, next best action, it all sits in the cloud. So we put one instance of Scrum on-premise, one instance of Scrum in the cloud, and let it communicate between them to run these federated queries. Think about it today. If majority of your data sits on-premise and you're insisting of doing the analytics in the cloud, you're forcing all the customers, first of all, to migrate the data to the cloud. So they come and say, okay, yeah, let's just lift and shift. Let's just take it and dump it. Take the, let's say, Parquet files and dump it on S3. Yeah, but you're just moving one problem and making another problem. It makes more sense to keep the data where it is today, and with time to migrate the data correctly and build new data models if needed, etc., etc. Scrum as well works on the edge in IoT, so as long as it has a GPU element in it, Scrum can work. For example, for a big insurance company, we tried to do it's not what we tried, we did an algorithm that calculates how driver drive, especially for new drivers. And before that, it was just average of speed that they used to do. Try every day to calculate average of speed, and it's a bit stupid, you know that. If you drove 100 kilometers per hour and 20 kilometers per hour, the average is 60. We actually managed to enable them to download the entire speed limits for that country into that small database that runs on that black box, and to in real time check every time the driver, every 10 seconds on the driver, if they're above the speed limit or below, and as well look at other elements like acceleration and stop, to get a profile of that driver, whether they're good or not, and transmitting the end of every day to the data center, green, red, or orange. And if there's too many greens during the month, then the next month premium basically drops by 40–50%. This is really how we can take it. Before that, it's just, I mean, the amount of data those IoT devices generated, it was just, that's the reason why they did averages. Similarly, with predictive analytics for, let's say, maintenance, so IoTs for productions environment, assembly lines, you just ignore most of the data because there's so much data that those sensors give you, and you look into one or two parameters, one or two dimensions, rather than maybe asking each of these devices to query and give you a status, give you a result, what is that, if that sensor is good or not, and then aggregate that from all the other sensors on the assembly line. So the possibilities there with IoT right now, and we'll see that with 5G. 5G will really change almost every element of our life, predominantly because of IoT and the ability to put analytics, smart algorithm in all of these edge devices. Here's some examples, just a benchmark of a really large telco network planning. So calculated the network strength in every coordination. This is Germany, so 16.5 trillion records, really, really large data sets. Scrum on 3 different platforms with the native, the front on the platforms. On AWS you have Redshift, on GCP you have BigQuery, on Azure you have Synapse that actually collapsed after, I think, 8 hours, I don't remember after, which is probably not surprising, you're right. And you can see that not only that we're really good in the ingestion is really important, especially when you're moving data from one place to another. We can get on the Scrum about 3 terabytes per hour per GPU. So if you have 4 GPU, 12 terabytes per hour ingestion. You don't believe me? Come to our booth, I'm going to show that to you. Querying time, you can see like with GCP we got about 50% of querying time. And as well, Scrum is really good at compressing the data because we have so much GPU power, we have brute force, so the data is only compressed when you need it. We don't have indexes in Scrum, we work in a metadata, so we have data in the blocks, and skip it, come to our booth, we explain it to you, but as a result of that, we're really good at storage, we're really good at how we store things, and it is really fast because we only compress what we actually need for the query all the time. And as a result of that as well, the cost, if you see, in most cases is between 25% cheaper or 60–70% cheaper. So if you're running BigQuery today and you want more power at much lower cost, come and talk to us, okay? I can give you so many other use cases. We have as well at the booth explanation of how this use case is built. If you want to see the details and the number behind that, please come and have a look at the details. So what does that mean for data scientists? So first of all, when you're modeling, when you're building the model, you directly get to the data. You can find those correlations, you can find those insights directly from data. You're opening a studio, you start writing SQL statement, you're getting immediately the results. Okay? So this is the number one for that. There's no need for data preparation. There's no need for fleet of data engineers that you need to rely on that. Or the whole issue of empowering data scientists. We are very passionate people. We really know what we want to do. We usually just need to rely on other people to do that. So the ability to basically do and run it very, very quickly, it's the number one thing. Then, training of the data. Once you build a model and you think the model is good, you want to train that data. And training data, you probably know, it's like availability, the difference between 90 to 95%, it's not 5%, right? It's millions, billions of records. And the ability to take the data from GPU to GPU without going into memory. You're again bypassing the memory issue and going directly from building building a result set and pushing that result set directly into the model, you're accelerating training. This is really important. We have, for example, for cybersecurity, for networks, for detection, and you really want to be able that once you find an anomaly and you train the model to anomaly, that automatically it will start activated and work. So again, we're moving all of these latencies in the process, because today if you build a data set, you build a result set, then you need to start pushing it to the model. And even if the model runs on GPU, you'd go for the memory and you go for CPU with all the hinders and all the problems, so you're probably going to really reduce your bandwidth there. No SQL joins limitation. So if you try to enrich data in training, this is really, really important. And any kind of aggregation or pre-compute that you need to do, you can do it at a really large scale, really complex. Again, come to our booth, we're going to show you that. And the last bit is all about basically integrating the models and making them to work in real life. How many of you traveled abroad and used your credit card and maybe it was flagged as a maybe suspicious transaction, but you got that 2 days after you done the transaction? You really want to get that at the moment, or 5 minutes, 2 minutes near real time of that transaction. Or if you've been on booking.com and you booked yourself into Amsterdam, and maybe 2 weeks after that you get on booking.com email, oh, best deals in Amsterdam. Yeah, but I already booked just hotel in Amsterdam, so why didn't you send it to me? Why, when I was on the website and was looking, didn't you pop it that? And this is really the whole move to near real-time analytics. It's really large scale, and this is basically what our technology is enabling doing. Last bit, I want to just very quickly tell you a story about a big bank in Netherlands that we helped them after COVID to look into fraudulent payment transactions. So they had a model that we did not build a model for them, and COVID happened. And COVID kind of changed the whole picture. Well, first of all, the volume of transaction really jumped to a much higher level, and then the difference, you know, of the sophistication of the fraud got a bit more interesting. And we managed to, basically saving them a lot of money, we managed to reduce 46%, 48% the transactional fraudulent, and we managed to help them to do the aggregation from about 12 hours. So they were catching up with things to around 40 minutes. And more importantly, so this is very high level, the architecture there. Once all the data events basically came into the system, there was some sort of in-memory models that tried to do this aggregation. It was too much data for them with COVID, so they could not basically run the model. So they start running simulations, start taking part of the data, running simulation. We've all been doing that, right? So it's nothing new. This is what you do when you can't access all the data. And that took 12 hours. So basically, it was inferior model, inferior sensitivity for the model, and partial data. We managed to turn that to, we just took exactly the same data pipe. We just added another step in the data pipe between the data sources and the model as current to basically do this aggregation, so the data model doesn't do the aggregation, and it sends it directly from GPU to GPU to the data model. And we reduced that from 12 hours to 40 minutes, which means that we can actually process the whole data sets and get that accuracy. This is how we managed to almost 50% cut them the fraudulent cost. I think it was 18 million euro worth of cost saving in 1 year. That's it. we've been around for 12 years. We have really large enterprises, really large names. We have use cases from a variety of industry. Talk to us. We're very happy to help you there. Come have a look at the demo. If you want to test drive it, come talk to us. We're very happy to roll you into some sort of a trial and buy. We'll give you some data scientists and data engineers that can help you look into your use cases. Thank you very much. Any questions? No? Enjoy. Thank you.